like decomposition. So in the simplest sense, somebody look at this right now and tell me what is decomposition in a scientifically defined way. Cellular respiration is part of it. Someone said oxidation. Cool. Who said oxidation? Awesome. Oxidation, absolutely. So what you're doing is, what is this carbon atom right there? It's reduced. It's reduced. Good. Nice, rich. That's glucose. Absolutely. Somebody said glucose, I think. That's glucose. It's reduced. This is why we take it in the form of a bagel in the morning. But it's also a major constituent. If you don't remember this, let me remind you, cellulose, which almost all plant matter is, not completely, cellulose is just a polymer of glucose. So bacteria have the capability to break up cellulose, break up that beta-1,4 bond across those glucose molecules, and turn it just into cellulose, and then break down that cellulose. And then use that glucose as an energy source. Okay. Bacteria can do that, fungi can do that. All right. You and I cannot break down cellulose. All right. And in fact, that cow that I just showed you in the last slide can't break down cellulose either. So the cow keeps symbiotic microbes in its gut. Protozoa and bacteria, all these cool guys in there, archaea, that can break down that cellulose, release those glucose molecules, and go through that metabolism. Without symbiotic bacteria, that cow wouldn't last very long because they eat grass, right? Hay. All right. So decomposition is just the breakdown of a glucose molecule, the oxidation of a glucose molecule, releasing carbon dioxide in terms of cellular respiration, and in the process, releasing a lot of energy. And please tell you what part of metabolism that is. From the metabolism lectures, what is that? Glycolysis is certainly part of it. Absolutely, it is catabolic or anabolic. Catabolic, the release of energy, the breakdown of the valuable molecule and release of energy. Okay, lignin degradation is a little bit different. So let me define what lignin is for you if you don't know. Now let me let you define. Anyone know what lignin is? Again, there's a couple people in the room. I know you know.
It's rigid, very hard, and it's hard to decompose.
Absolutely, Ashton. Great. Okay. It's rigid, it's hard to decompose. And where is it in the biotic world? It's rigid and hard to decompose. Rigid is the key word here. Where is it? Trees. Excellent. Terrestrial plants. Terrestrial plants are all trying to get up to the light. So the molecules, freakish oversimplification, the molecules are really volatile. And lignin allows plants to stand up tall. It makes them rigid. It's also a really nasty, big, complex molecule. It's incredibly hard to break down. So let's just quickly look back at this leaf. Okay? This leaf is breaking down all its soft tissue, but leaving behind the vascular structures, the real rigid parts of that leaf tissue. When a tree falls in the forest or in a storm in New Jersey and it's decomposing on somebody's front lawn, it all breaks down first. The first things to break down are all the soft leaves, etc., things like that. The cellulose breaks down first, etc. The lignin gets left behind because it's really hard to break down. Well, who can break that down is fungi. There's specific groups of fungi that can break that down. So lignin degradation is almost exclusively a fungal process. And we're expending a lot of energy. It's a very narrow group that has the enzymes to get energy out of that big nasty molecule. So think about it. You don't need to write this down. You can put your pens down for a second to help you understand why I'm giving you this information this way. We're thinking about the first slide I gave you was a picture with the tree and the rabbit and the hare. And I said, but let's think about this from the perspective of the role of microorganisms. Think about all the trees and plants on this planet in the terrestrial environment, and if they all have lignin and we didn't have a microorganism that could degrade lignin, what would we be sitting in? A lot of trees, a massive, massive carbon sink, okay? A huge storage of carbon that wasn't otherwise getting decomposed and respired back to the atmosphere as CO2. All right, so you need need then to, if we didn't do that, then it would completely upset the balance. We'd never have any more CO2 back in the atmosphere if there were more photosynthesis. Alright, so, this is just redundant with that first slide. It's another way to look at it. Carbon moves through food webs. So this is just kind of redundant with that first slide with the hair and the links. But it summarizes a lot, and it shows it to you in an aquatic setting, and you can kind of get a good snapshot of it. Where the sun energy fuels the capture of carbon dioxide into pretty green plants. Alright, photosynthesis. And there's all kinds of organisms that eat those green plants. Alright, those organisms release CO2 back to the environment, okay, etc. So don't fret about this slide too much as you study. It's just more a big picture to get a look at the big picture of how energy gets captured into microscopic plants, okay, and the little things that eat that, and then they die, and then the microbes eat the things that die, etc. Okay, so just a reminder of the carbon cycle. So what we went over is, we went over photosynthesis, right there. We went over decomposition, right there. Okay, and that's an aerobic environment. In an anaerobic environment, this can happen. I didn't go over the specific processes that make it happen, but it certainly can happen in an anaerobic environment, particular cyanobacteria don't necessarily need oxygen. Alright. And then you can have the anaerobic degradation of organic matter right here, either releasing CO2 through a fermentative pathway, or also the process of methanogenesis. And I talked about that with respect to things like rice paddies, salt marshes, and flooded lands like the Meadowlands. And the guts of, particularly famous for that, are the guts of ruminant organisms that are very anaerobic, cows and sheep. Okay, so before I move on to this, how this applies environmentally into climate change, questions? Is anyone confused? Is anyone confused that wants to admit it? Okay, so let's think about how this applies. Just this is, one time, one or two times in your career here at Montclair, you're going to get to hear about why do we care about these things with respect to climate change. So as I started out this part of the lecture saying that so much of the global carbon cycle is microbially driven. And I gave you one little slide back there showing that photosynthesis is so heavily dominated on this planet, even though we see all the forests around us here in the terrestrial land because we're terrestrial organisms. Most of it that's really ongoing is out in marine environments and aquatic environments with floating phytoplankton. Alright, organisms that float up on the top of the water and catch the sunlight. And that turns over incredibly fast. Huge amounts of photosynthesis go on there. Alright? So that's a microbial process, etc. So what's happened is, what we've done is we have all these very natural conversions of carbon dioxide into fixed form, and then the respiration of that back to the atmosphere that have been ongoing on this planet for billions of years. But most recently, we've started taking some of that stuff like methane gas, etc., coal, things like that, and we've started burning them more frequently. So we basically short-circuited the natural carbon cycle and started increasing it. And you can see that in data, very real data that shows through time, as we've gotten about at the time of the Industrial Revolution, about 1800, the emission of things like methane and carbon dioxide just shot way up above the normal biological baseline level. All right, and when those molecules get into the atmosphere, they trap the sun's rays, the greenhouse effect. They're trapping the sun's rays and not allowing them to bounce back, causing warming in some places. Global warming is kind of a good catchphrase, but not always accurate in every description of what climate change is really about. Climate change is really about a word. It's going to warm in some areas and cool in others. So it's basically because we've had this huge increase just with respect to the carbon cycle. This relates to the nitrogen cycle that's beyond the scope that we need to know for this class. These huge increases in methane production as well as carbon dioxide production. Carbon dioxide production is just the burning of fossil fuels, burning coal, et cetera. Methane production has gone up just because we've really increased the intensity of our agriculture. Millions and millions and millions of cows and sheep on this planet. Everyone talks about New Zealand as being this, great pristine landscape, but then a lot of people also joke about it as being this horrible environmental nightmare because they have so many sheep on New Zealand that you can actually quantify their contribution to the global carbon budget because of all the amazing amounts of gas released by their sheep. So, methane is a huge problem. Things like rice agriculture contribute to that. Alright, and how this feeds back to climate change and how it relates to microorganisms is that you have something that looks like an Arctic tundra area, okay? You have a lot of carbon stored in that soil. So we have carbon stored in that soil in a frozen state normally in the Arctic. As the Arctic starts warming, that carbon is stored up in the Arctic is going to start to degrade and decompose. And it's frequently a waterlogged environment too. So not only are you releasing carbon dioxide in terms of aerobic glucose degradation and degradation of that organic matter in the soils and the sediments there, but you also have a lot of anaerobic degradation of that organic matter. And that's being carried out by microbes in the sediments that were previously, for thousands and thousands of years, completely dormant because they were frozen. So now, for a couple of months every summer, for whatever started to extend it a couple of days, to a couple of weeks, whatever, the summers are getting a little longer and a little warmer, having more time for those things to decompose and degrade as it warms. And so as that happens, it's releasing huge amounts of previously stored carbon. Okay? And so what that does is it just adds more greenhouse gases. That's one example of how we're adding a lot more greenhouse gases and why the Arctic is warming more than it ever has been. So another example of this is also in terms of agriculture. You can have a whole lot of carbon stored in the soil, say in grassland. You go till that up to go plant a cornfield, and you're releasing a lot of organic matter. In the process, the microbes get stimulated, they degrade it, they release CO2 into the atmosphere as well. Okay, reasons for carbon dioxide, burning of fossil fuels. You guys all understand that. Deforestation, taking carbon that was stored in a forest and then burning it. And then conventional agriculture like plowing. Going back to what I was saying here is, in the process of thawing boreal regions and Arctic regions, and in the process of plowing once pristine fields, you're releasing a lot of carbon to the atmosphere because you're stimulating the microbes there, either by warming them up in this environment or by aerating them as you turn over the soil. Consequences are temperatures are rising. Yes, I want to go ahead and wrap this up. Temperatures have been rising steadily, and we can correlate that with increases in greenhouse gases. Okay, and more consequences, last thing. I'll just say this, and you don't need to worry about it too much for an exam. It's affecting ecosystems in terms of the animals. For instance, there's a whole lot of research being done, research at this university being done on amphibian decline, because frogs and other amphibians in this area, newts, so they're starting to get different diseases. They're getting different diseases, and the thought is that we're just getting just the tiniest bit warmer that's allowing different microorganisms to exist and infect things. We've seen this in a lot of other ways too. I should dedicate an entire lecture to that. It's really interesting. Part of the reason for amphibian decline is associated with global warming and a shift in the distribution of disease-causing organisms. Okay, so we'll pick up there on Thursday. And I want to make sure everyone has plenty of time for their exam. Okay. Alright, so nobody else can do it, then it's good, you'll have plenty of time. The exams. Averages, I think one class was like 75, and then the second class was like a 79. So the class averages were very high. There were very few Fs. I think there were maybe 2 Fs, and higher than 48 of you. And there were, I wish there'd been more A's. There was probably only about half a dozen A's. On the first test, I had closer to 10 to 12 A's. So there were only about half a dozen A's this time, which is okay. I like to see a couple more A's. But I also know we've all had a lot going on in the past few weeks. It's been successful in looking at hard setting. And then not to mention the delay from getting the material and having to put down on the test. As I said, the rest of the course, we'll talk about this more next time. I'm gonna cut the immunology lecture just to keep the content so we can get to the end of this class. And then we will, probably have a slightly shortened, like maybe only half lecture review session. I'll see how I can get that to fit in, review session for that final test. So, I think the low was in the 30s, the high was I think in 96. A whole lot of B's and C's, which I just didn't show. A whole lot of B's and C's. Let me see if I have. We call these out.